A modern retail brokerage experiences traffic variance unlike almost any other software application. A routine morning handling 100,000 requests per second can instantly surge to over 750,000 requests per second, driven entirely by unpredictable social trends and market volatility. When confronted with a massive traffic spike, the standard software engineering reflex is to scale horizontally. You decouple the application domains into separate microservices and automatically spin up more Kubernetes pods to absorb the load. For large portions of a brokerage, this works perfectly. Client registration, identity verification, and bank integrations scale across thousands of distributed servers. This distributed cloud pattern fails when applied to the platform's critical execution path. This flowchart illustrates the problem. The bottleneck at the order execution node is caused by a regulatory mandate known as price-time priority. If two users submit market orders to buy the exact same stock at the same price, the order arriving first executes first. Under Amdahl's law, this means the order book for a single financial instrument is strictly serial. Because each trade modifies the available liquidity for the next, the matching process cannot be parallelized across multiple servers. High-throughput brokerages scale horizontally across different symbols, but optimizing execution within a single symbol requires working against the serial nature of these physics. Protecting that strictly serialized order book requires an architecture that isolates the asynchronous read path from the deterministic write path. The read path carries immense weight. The platform must ingest and broadcast millions of price updates per second from external exchanges. This dual pipeline diagram shows market data distribution. The top path handles sub-second ingestion. Raw ticks route through Go or Rust services into Redis and directly to screens via WebSockets. Simultaneously, these ticks fork into the analytics pipeline, routing through Kafka and Flink for state aggregation. This analytics pipeline continuously computes the sliding indicators and historical candlestick charts rendered in the trading interface. But rendering charts is only half the read path problem. Historical data shows that up to 90% of active retail users do not trade on a given day. Instead, they constantly refresh their apps to track their portfolio's profit and loss. Computing these holdings by running SQL joins across the portfolio and position databases on every single refresh would saturate the database layer in seconds. Instead, the system computes a cryptographic fingerprint, an E-tag, of the user's holding state. By caching this E-tag in Redis and serving it directly, the platform absorbs massive read-heavy traffic without touching the core transactional databases. The write path begins when a user taps Buy. That action generates a fixed protocol message called a new order single, which enters the brokerage network. Before that order can enter the market, SEC Rule 15C3-5 requires the broker to run pre-trade risk checks, verifying the user's buying power and margin limits. Querying a distributed database over the network to check these balances introduces unacceptable execution latency. This diagram illustrates the structural solution. The risk check module is deployed as a daemon process on the exact same physical hardware node as the order management system. To communicate, these systems use local-host Unix sockets, allowing data to bypass the operating system's network stack. By keeping the data path entirely localized, this architecture evaluates complex margin and risk parameters in approximately 4 microseconds. Moving risk data out of distributed databases and into localized memory guarantees users operate within their limits without slowing down the trade execution pipeline. Once approved, the order enters the core of the platform, the order matching engine, where price-time priority is enforced. To achieve deterministic execution, engineers abandon standard multi-threaded thread pools. Utilizing multiple threads introduces CPU cache invalidations, context switching overhead, and lock contention. Instead, the matching engine uses a single threaded loop. It isolates a single, highly optimized physical CPU core to process every insertion, modification, and cancellation for a specific stock. Using thread affinity APIs, specifically commands like pthread-set-affinity (NP), the software pins its application thread to that dedicated core, blocking the operating system scheduler from interfering with its clock cycles. A bare metal single-threaded C++ loop sits within the globally distributed cloud-native trading platform, running independently of the external operating system. Inside that loop, the engine's sole task is rapidly inserting, deleting, and matching resting orders at specific price levels. This diagram represents a traditional tree of lists order book. Each price level points to a linked list of resting orders, scattered across random locations in the system's memory. Traversing these scattered pointers requires the CPU to pull from RAM, resulting in cache misses that destroy throughput under heavy load. Modern architectures replace this scattered layout with priority-indicated nodes, snapping the data structures into tightly packed, contiguous memory arenas. This contiguous layout requires zero runtime heap allocations. Memory access becomes predictable for the CPU cache. With the memory organized, the engine must instantly find the next active liquid price level in the order book once a trade executes. Iterating sequentially through every possible empty price slot to find the next active order would waste critical microcycles. Instead, the engine maps active prices to a binary bit set. A value of 1 indicates active liquidity. A 0 means the price level is empty. The software utilizes hardware-level bit scan intrinsics, specific C++ commands, to count the trailing zeros in that bit set. This command allows the CPU to locate the next active price level in a single instruction cycle, bypassing loop checks. Millions of matches per second depend on data structures that align perfectly with the physical architecture of the CPU cache. Once an order matches inside that C++ core, the execution is irreversible. That data must now re-enter the horizontally scaled distributed network. The execution report flows immediately into the ledger and portfolio systems to update settled holdings and initiate clearing operations. Look at this double-entry ledger architecture. Rather than relying on standard database overwrites, data blocks are strictly appended to the end of a chain. Any queries regarding account balances only read from the established historical chain. Specialized financial databases, such as Tiger Beetle, utilize this explicit write last, read first pattern. By separating the ingestion of new transactions from the reading of current account balances, the database natively enforces financial limits without bottlenecking the high-throughput event stream. A modern brokerage exists in a state of deliberate duality. It requires massive asynchronous orchestration to handle millions of client connections and broadcast real-time market data across the globe. Yet the core matching engine demands synchronous, single-threaded execution to ensure financial determinism. Scaling a brokerage beyond the limits of average traffic requires an architecture shaped by the physical and mathematical constraints of the execution path. A retail brokerage functions because it engineers a highly distributed, cloud-native shell around a hardware-sympathetic core, isolated from the distributed environment, ensuring that when 1 million users tap trade at the exact same moment, the system never blinks.